Let's start one more lecture on these fundamentals and biomedical application of quantum science. Well, today, last lecture, we went through the atom, where we have a center of force and electron that's bound to it. Today we're gonna double the number of nucleus. So we're gonna have two nucleus and an electron trying to bind this nucleus together. This is what we call molecule. So the molecule is a situation where many of those center of forces, which is positive charge, are together, and they are surrounded by an electron cloud, which is here. The electron cloud actually distribute among the nucleus and the distance between them and the space between them. And as a result, it turns out that the electron itself can bind this together, because naturally the two nucleus wants to repel each other. They are both positive. But if they start to get too close together, they repel. But when they get far apart, the electrons somehow win the force and make them to come back. So the electron is actually the glue for the two nucleus, right? The electron is the element that maintain the molecule together. So the molecule stays together because the electrons make the bonds. And this, we have to understand how is that done. What is the energy that's involved in this situation, and so on. So today we're going to explain to you the main features. You know, we're not going to go in deep detail on the calculation, because this is not the main goal of this course. The main goal is to give you some insights for what's going on in this situation. But of course, we know that molecules has more applications than the atoms for the biomedical applications in general. You know, we have molecules everywhere, and they exchange electrons. They do all kinds of things, changing the configuration of the nucleus, changing the amount of nucleus that are there in chemical reactions. So all these things they do, and that make a lot of metabolic reaction that keep us alive. Okay, we're going to start considering what is the energy that is involved in this process, right? Because we know that the electron, because it is bound to the nucleus, it has some energy. And this energy has a value. But then there are some other energy channels in here that we can consider. So we're going to do all this in this lecture. So the first thing is look to the molecule. Actually, the two nucleus are separated by a distance that we're going to call A here. So A is the distance, internuclear distance. And the electron has to be around this part. So the electron has to be around this. So the delocalization, or the space occupied by the electron, is on the order of A in one dimension, right? So we have a delta X, let's say, about A, because the electron has to be here. If the delocalization on the electron is A, and we consider this as the minimum energy, then there is a kind of uncertainty on the localization. And this uncertainty is exactly the space, more or less, occupied by the electron. But as I said, we are in the minimum energy, so that is also involved an uncertainty in the momentum. And the combination of those uncertainties is what determine the energy of the electron in this configuration. Okay, so if you consider delta X about A, the uncertainty in position, and delta P about P, the uncertainty in momentum, we know by the uncertainty principle that the product of those uncertainties is on the order of h bar. Therefore, we have a kind of value or order of magnitude for the momentum. And the momentum is square divided by 2 times the mass give us the energy. So the energy of the electron in a chemical bond, or for the electron occupying this distance between the two nucleus, right, is on the order of h bar squared divided by 2ma squared, which is basically this p squared divided by 2m. Oh, what about the electrostatic energy, the energy that the electrical interaction? Well, it's the same order. We can prove that they are in the same order. Okay, so that's the order of magnitude. Now, we know what's the mass of the electron. We know what's A is on the order of angstrom, right? And we know what's h bar, the Planck constant. The mass of the electron is on the order of 10 to the minus 27 grams. The distance between the two nucleus is about 10 to the minus 8 centimeter. And the h bar is on the order of 10 to the minus 27 erg seconds. So all this together in the same unit, it turns out that we can put this on this expression. And we get an energy, which is on the order of 10 to the minus 11 ergs. Right? Because we are working the CGS. And this turns to be about 10 electron volts. So the energy that the electron is bounded to the two nucleus. So the energy that's contained on the nucleus, on the electronic cloud that makes the molecule to exist, is on the order of a few electron volts. So that's a nice energy that is present on this chemical, let's say, bound of the two nucleus, making the molecule. But this is not everything. We have more than the electronic energy. When you look to the molecule, look into this molecule, we see that there are more energy besides the electronic energy, because the two nucleus, they have mass. And due to the mass of the nucleus, there are another channels of energy that can be existent in the molecule. So we have basically, because of the mass of the nucleus, and because we are bounded by the electrons, so this here we are representing by a kind of spring, right? So we have a spring which has some constant, and this is binding the two mass together, the two nucleus, with mass capital M. And because this mass exists, there are vibrations and there are rotations. Two mass together, they have an energy of vibration. And we all know the energy of vibration. The energy of vibration is a combination of the energy storage here in the spring, plus the kinetic energy of the masses. We know how to solve harmonic oscillators, right? So here we have energy that's coupled to this system, and it is contained in this degree. Vibration is something very important on the molecules, because as we're going to see, many things will happen due to the vibrations. Now, because we have this two mass, we have also the possibility of rotation. And you all know that mass rotating is kinetic energy in the form of rotation. And then we have energy, and we know that the energy of the rotation is basically the angular momentum squared divided by 2 times the inertia momentum of this, or the momentum of inertia. And the momentum of inertia depends how the mass is distributed. Normally the momentum of inertia in this system here will be basically 2 times the mass times the position of each mass square. It turns to be, the momentum of inertia turns to be ma square. A is the distance between the two mass, and half of it is the distance from the center of rotation. And that's how we evaluate the momentum of inertia. Okay, so You see, now we know that the electron itself has some energy, and we just saw that was on the order of 10 electron volts. Now we want to know what is this energy, what's the value of those energies. And to do that, we needed to come and say, well, this is like a harmonic oscillator, right? So this harmonic oscillator keeps the electron bound to the nucleus with the same constant, which keep the two nucleus together. So we say that the frequency of oscillation for the electron that's bound to the nucleus is basically a constant divided by the mass of the electron, root square of that. So we are evaluating the energy in terms of frequency, but we know that energy is h bar omega. So evaluating frequency, we are somehow evaluating energy too. So for the electron, the frequency of oscillation, if we see the electron bound to the nucleus and oscillating, is root square of k over the mass of the electron. But when we look to the nucleus themselves, the force is minus k times now the distance between the nucleus, or the variation. And the vibration in this case is a frequency that's given by root square of k divided by the mass of the nucleus, not the mass of the electron. As a result of that, when we take the ratio, which is basically taking the ratio of the energies, it gives us a ratio which is the mass, the electronic energy, or the electronic frequency, divided by the vibrational frequency. Is basically the mass of the nucleus divided by the mass of the electron, root square of that. And this is 10,000 times more than this, which gives us a factor of 100. So the energy contained in the vibration is 100 times less than the energy contained in the electron themselves. So the chemical bond is actually the main source of energy of a molecule, because all the energy is there. And therefore, we already evaluated the electronic energy. So we can come with the result that the energy that's contained in the vibration is basically 1/100th of the energy contained in the chemical bond, right? And this is about 0.1 electron volts. So that's the energy contained on the vibration. So the molecules want to vibrate, and of course we will be modified by the electron too, and this is on the order of a fraction of electron volt. So we already seen that when we compare the electron that's binding the two nucleus together and the vibration, the energy is preferable on the electron that's binding. The chemical bond, which is the name you give to this cloud, right, contains most of the energy. And for most biological process, that's the main source of energy that we're going to have, is the energy contained on the electron themselves, on the chemical bonds. Not in the vibration, but the vibration is very important. So we know already that the vibration is 1/100th of the energy of the electron, so it's 0.1 electron volts. What about the rotation? Well, to see the rotation, we gotta come, imagine the system, calculate the momentum of inertia, and this is what we have done. I already showed to you the momentum of inertia is the product of each mass by each position square. We have two masses separated by a/2. So this gives us a moment of inertia, which is about ma squared divided by 2. Right? And the angular momentum for this molecule gotta be on the order of the h bar, which is the traditional quantum of angular momentum that we have, especially in the atomic and molecular level. So with this, we can calculate what is the energy in the rotation. And the energy in the rotation is basically the energy in the rotation which I am also call h bar omega rotation, because we can know also the frequency of rotation, is h bar square, which is the angular momentum square. Remember, this energy is L squared divided by 2I. L square is h bar square, and 2I is just ma square. So the energy of the rotation is h bar square divided by ma square, which of course can give us energy. So if we multiply the electron energy, the electron frequency, and the rotation frequency by h bar, we have the ratio between the two energies. And the ratio between the two energies is the energy of the electron that we already calculated before. That's like h bar square divided by ma square, remember, by the uncertainty principle. And now we have h bar square divided by m, the nucleus mass, a square. Almost everything cancels except the m's. And the rotation energy is the ratio between the nucleus mass. The electronic energy to the rotation energy is proportional to the nucleus mass to the electronic mass, which is about 10 to the 4. So we already had 10 electron volts for the electrons, for the chemical bond. So now we have 10,000 times less. And this gives us an energy for the rotation, which is 1/1000 of electron volts. So you see, in terms of energy, even though we have all those degrees that can have energy, the electronic is the most important for the molecule. So there is where the most quantity of energy. And then we have some in the vibration and some in the rotation. So even though the chemical bond is the most important source of energy in the molecule, there are still energy in the rotation and the vibration. Even though that energy is smaller, as we saw, that's an energy scale. That's the energy scale, and we have the most energetic part of the molecule, the electrons, which is the chemical bond. And then followed by vibrations, which is the freedom for the nucleus to move each other. So this is vibrations. And we have finally the rotation, which much less energy. And this is 10 electron volts, this is 0.1, 1/10, and this is 1/1000 of electron volts. If we consider that the energy is basically h bar times the frequency, we can characterize this frequency as part of the electromagnetic spectrum. We can make comparison. Because as we're going to see further, it's through electromagnetic waves that we're going to move those charges, that we're going to excite those energy modes, let's say, of the molecule. So this is on the microwave. That's why microwave is good to excite rotation. This is in the infrared. That's why infrared means the vibration of the molecules. And this is in the visible UV. And that's why we see the things the way we see, with color and everything. Right? Now, in terms of total energy for the molecule, we have then to consider, even though they are different in different magnitudes, somehow those are freedoms for energy to be located. And then they are part of the energy. They must be part of the wave function. They must know how to contribute to the overall energy. Vibrations, we know the harmonic oscillator. Vibration is always almost like harmonic oscillators. And this is a h bar omega times a quantum number plus half, because there is a 0-point energy even in the molecules. And the rotation, we saw already the rotation of the electron around the nucleus, and we know that L square goes like a quantum number times the quantum number plus 1. So the overall result of having these 3 degrees of freedom in the molecule for accommodating energy is that the overall energy is the sum of the electron plus the vibration, and here I put h bar times the frequency of the vibration times v plus half, and this v is the vibrational quantum number. Right? This is the vibrational quantum number of the molecule. But we have also the rotation. The rotation is basically the angular momentum divided by the inertial momentum. Here I put mu, which is the reduced mass, because I already composed the two mass rotating around the center of mass. And the angular momentum for the molecule square is equal h bar square times an integer number and an integer number plus 1, because this is as was in the atom, but we call this L for the atoms. F is the rotational quantum number. And so we see that they all be quantized in the molecule. We're going to have a quantization of the electrons, so they will be bound by two nucleus, but there will be all the Coulomb interaction there. They have the vibration, and they have the rotation. So this is the important point of this lecture, is make sure you understand that when I make a molecule, I have energy in the electron cloud, which is the chemical bound. It's the chemical energy mostly used. But we do have a vibration, and then we have the quantized vibrations, and then it's like a harmonic oscillator, and we have a rotation, which is like a rotor. You know, rotor is very interesting because the angular momentum is always like this. So we have these three components of energy. And of course, when we make an energy diagram, we have to consider everything. We have to consider the electronic level. On the top of it must have a lot of vibrational levels, and on the top of the vibrational levels must have rotational levels. So when you look at molecule, you know, the diagram of levels or the energy levels looks very much like this. You have basically an electronic level. I'm putting blue. And then on the top of this electronic level, we have a lot of vibrational levels. All those are vibrational levels, which is like one tenth of energy. Yes, it was 1/10 of electron volts of energy. You know, this distance here is on the order of electron volts. I put 10 electron volts, but the distance here is like 0.1 electron volts. Right? So we have all the vibrational levels. And on the top of the vibrational levels, if we look there, we have the vibrational levels in red. So let me put here. Here is a vibrational level. This is another vibrational level. We have on the top of the vibrational levels what we call the rotational levels. Right? So actually the molecular spectrum of energy is a composition of electronic states, vibrational states, and rotational state. And you have to understand that the electronic energy is what keeps the two nucleus around. And I want to demonstrate that for you. I don't want to make a lot of calculation. I don't want to make your mind confused, but we need to find out how, if everything we're saying is true. And to do that, we have to prove that the energy that keeps the nucleus together is the electronic energy. Okay, so I'm going to start with the Schrödinger equation that we all know. And we're going to consider all possible energies that are involved. So the energy that are involved is the electron energy, which is this part, and the interaction with the two nucleus. So this is the electronic energy. It must be here. Because the electron now it interacts with one nucleus and the other nucleus. So I have two coordinated of the electron with the two nucleus. And this is negative because they have different charge. So this plus this somehow is related to the energy of the electron together with the nucleus. Then we have a repulsion between the two nucleus. This is the repulsion. And we have the movement of the two nucleus. This is related to the nucleus mass and the interaction. So we have the repulsion between the two nucleus. We have the attraction of each nucleus with the electron, and we have the motion of the nucleus. And because this everything is three-dimensional, all the rotation will be involved in here, in this momentum. When this nucleus is moving like this, right, if you have the two nucleus, and they are moving, momentum are like this, they are rotating. So this must be here, must be here. So this is all the energy that we have to consider, and as we remember, each term of this energy is an operator, is a mathematical variation of the wave function, if you want to determine the wave function. So based on this energy, we're going to construct the wave function for this. In the place of the, let's separate first, put all the nucleus together. So here we have the momentum, two momentum together, and I reduce to the reduced mass. So this term here comes to be this term here. So we have one term for the kinetic energy of the nucleus, and I use the reduced mass. Remember, the reduced mass is the product of the mass divided by the sum of the mass. So it turns to be half in this case if we have what we call homonuclear molecule, which is the two nucleus are equal. And then we have the repulsion between the two nucleus. So this part times the wave function plus the repulsion times the wave function. Now I have to add here the kinetic energy of the electron, which is this part. Here is the kinetic energy of the electron. And the interaction of the electron with the two nucleus. Of course, the electron is here, so we call R the overall position of the electron with respect to the center of mass. And then I have one electron which is being attracted to this guy and one to this. And R1 and R2 is replaced here by R plus or minus R, capital R, which is this one, capital R over 2 is the position of the two nucleus. Right, so we have plus and minus. So what we end by having is then the nucleus part, which is the kinetic energy plus the repulsion, and the electronic part, which is the kinetic energy of the electron and the interaction with the two nucleus. And this must be E times the wave function. So this is the Schrödinger equation for this case. Because the Schrödinger equation is all the interactions, all the energy times the wave function, but this interaction must be placed in terms of the real variation of the coordinates, because that's how energy is extracted from the wave function. The kinetic energy is the second derivative of the space, and so on. Right. So basically, and this energy contains all the terms that I just discussed with you: electronic, vibrational, and rotational energy. As you can see here, there is a kind of coupling between the electron motion and the position of the electron, because when the nucleus are moving around, R is moving, and this affects a little bit the electronics, of course. But the way I wrote it here indicates, at least, that we can somehow separate these motions, right? We can consider that the nucleus varies, the energy and the nucleus is motion affects very little the electronic energy. This is an approximation. And then we can propose a solution for the wave function psi, which represents the wave function of everything here. Everything. It has to contain the nucleus Now, psi contains the electron and the nucleus. Contain everything. Right? So I hope you follow how I build up this equation, which is the energy. Normally we refer as the Hamiltonian, but we're not exploring these terms very much in this introductory course. So that's the energy, and the operation, mathematical operation in the wave function that's represented by the energy terms is equal to the energy times the wave function. That's the way we construct the Schrödinger equation anyway. So having the Schrödinger equation for this, which has all the terms, the nucleus and the electronic, we can try to solve. So what's the solution for this problem? Well, the solution for this problem must be an electron part and a nucleus part. The nucleus part we're going to call D. And the electron part we're going to call phi. And there is a sequence of quantum numbers that we're going to represent by lambda. And because there are many different solutions for this, you know, if the electron was fully separated from the nucleus, if there was no this R term here on the repulsion, then small r is fully separated from the big capital R. If that was the case, then we could really say that the solution will be the product of a wave function that represents the nucleus and the wave function that represents the electron. But we cannot, so we have to say that the electronic states, which will be represented here by phi, and phi will be basically the electronic spatial distribution we have, depends on the position of the nucleus, of course, and depends on the coordinate of the electron. Now, the nucleus, that function, which I call D, depends only on the distance between the nucleus, the nuclear coordinated. But we're going to insist that we can separate them. We're going to insist. We're going to say that the wave function is a superposition of the electronic states, which coefficients depending on the position of the nucleus. And we're going to say, well, let's go to the electronic part only. This is true if in what we call the Borobenheim Approximation. What is the Borobenheim Approximation? The Borobenheim Approximation, it considers that the variation of everything with R is small. So it's like saying that the wave function of the electron almost do not vary very much with R, or the derivative of this wave function of the electron with respect to the nuclear coordinate is basically zero. This is called the Borobenheim Approximation. And if you want to just think easy, it's like if the nucleus are stopped. They don't vibrate in the first moment. Then we consider only the nuclear part, the electronic part, I'm sorry. Considering only the electronic part, we take that equation before, we separate, we take only the electronic part, the electronic kinetic energy, and the electronic interaction with the two nucleus, which is the attraction of the electron with each of the separated nucleus, right? And we had a figure for explaining this. And this must be equal to the energy of the electron times the wave function. Phi here is the wave function of the electron. This equation will generate a set of functions and a set of values. And this set of values are the possible energy of the electrons. We normally call the eigenvalues of the electron states, which will give origin to the chemical bond. Now we're going to do, let's assume that we solve the equation. We have phi. We put inside in here the phi's and the energies. And when we replace when we come to this equation and put the psi, but remember, psi has a phi on it, and we know the phi, all the electronic part will be what? The electronic part will be basically the energy. That's the equation here. Will be the energy of the electron times the d. Remember, so what I'm going to do is take this function, psi, which is the product of a sum of the product of different functions for the nucleus and the electron, and substitute in the full Schrödinger equation. But I already told it to you that I have a solution for this, which is E lambda. All this together gives E lambda, which is the solution for the electron, which is this equation. Well, you can multiply by d here, that doesn't matter. Any of those mathematical operations does not affect the d. So at the end of this calculation, we can show that the function for the function d, which represents the nucleus wave function, is given by the kinetic energy of the nucleus plus the electronic energy as a potential energy for the two nucleus. And this will give you the total energy, because that's the way we start the full Schrödinger equation. Right? So basically what I proved to you here in a very fast way is that the electronic energy is actually the potential that keeps the nucleus together. So the electronic energy, which has a dependency on the position of the two nucleus, is the potential that keeps these two nucleus together. So the electron cloud is as if there was a potential keeping the two nucleus together. And that's why they stay together. And that's the main of keeping together the two nucleus. Now, how is this energy? Of course, it depends on the nucleus position. So we're going to plot here how is the dependence. If I solve the equations, I'm going to get E of lambda of R, which is the electronic state, the electronic energy only. But the electronic energy only is the potential energy for the two nucleus. And if I look to the shape of this potential, what I get is this shape. The energy is not a single value, but has a R dependence. And this R dependence makes this interesting potential with a minimum, which is the potential energy for the nucleus. So the two nucleus is like they moving in this potential. Of course, we use there the reduced mass, so you can imagine like the reduced mass bounded to the center of force, which is the center of mass. And that is a position of minimum, which is normally where the molecule wants to stay. That's the average distance. This will be the A that we said in the very beginning, which is the rest position, let's say, or the equilibrium position. Now, we do have a depth for this potential, which I call C, and if you wanted to dissociate the molecule, you have to put this energy in there. So that's basically the energy that keeps the two nucleus together. This is how deep it is, how much energy they have, what's the energy that is in the chemical bond. So when we speak about energy in the chemical bond, we're speaking about the energy of the electron, because that is what keeps the bond. That is what keeps the two nucleus together. Okay, so we learned a lot today, but when we solve this equation, or better, when we solve this equation for E lambda, which is the electronic energy, we get a collection of energies, because this is the wave. There are many possible waves, many possible distribution of the charge. Then we have different E lambdas. And those E lambdas, they can have many different variations with the nuclear position. Depending on the nucleus position, different E. And it turns out that sometimes we get energies that goes like the one I just showed to you, with a minimum, which allow the nucleus to be bound together. So this is the origin of the chemical bond. But there are some dependencies of E lambda, which is the electronic energy, with the nuclear position R, which has no minimum. So repulsive. And this is what we call an unbounded situation. Those states allow the formation of the molecule. Those do not allow the formation of the molecule. And it turns out that sometimes, because I'm interacting with the electrons, I can shoot electromagnetic radiation on the molecule, and it goes from one state to the other. It can go from a state that's bounded to a state that's unbounded. This is a photodissociation of molecule. And it must be very important in all chemical reactions, including, possibly, the photosynthesis and things like this, where the energy of the light will come and make again molecules. Right? And that's why we live. So in many situations, promoting electronic states through a transition from one to the other, from a bounded to an unbounded state, we produce the molecular dissociation. So you see, you can manipulate this by manipulating the electronic states. And this is everything because the quantum mechanics tell us that what's keeping the two nucleus together is the electronic energy. This is the fundamental thing. The electronic energy is the binding potential for the two nucleus. And that's the origin of the chemical bond. Normally in books, they're gonna call this gerade and ungerade. It comes from the German to say things related to symmetry of the wave function and many things related to the two nucleus position. And we're not going to go in detail about this because we must cover some other things on this course. But it's impressive that the quantum mechanics explain to us how the two nucleus gets together. Even though being positive, the binding energy created by the electron creates actually a potential. And this potential is the origin of the vibrational levels. We saw there are vibrational levels. Where are those vibrational levels? They are here. Energies of the system in this. The two nucleus can be very little excited or more excited, and this is related to the vibrational. And where is the rotation? Well, it's also involved in this when we solve this equation. Where are the rotations, right? When we solve this equation, this Laplacian on the coordinate of the nucleus that we separate in the nucleus coordinate and the electron coordinate, it has angular dependence, right? A Laplacian in the space has dependence on theta and phi, all the angular coordinates. And those dependencies will create here a very interesting situation where the angular momentum and the rotation comes together. In fact, one of the reasons for this barrier here is centrifugal barrier. It's when the things spin around and there is a positive L plus L, F plus F plus 1, h bar squared divided by r squared. These are. So we cannot go. Well, we saw many things in this situation. Now the unbounded chemical, there are normally we call ligand and antiligand, right? And this means bounded and unbounded situation for the chemical for sticking together the two nucleus, making the molecule. But you have to understand that we can always promote the electron from one to the other state. And if we do that, the two nucleus fly apart because they feel just a repulsive potential. Because this value here actually is effectively the potential between the two nucleus. So, explaining all that I explained to you, let me put an expression for the energy of the system. As I told you, there is this part here, which is the electron, the chemical bond, and everything. That is the vibrational. Normally there are more things, so this is approximately. Because the nucleus now is going to vibrate. This potential is not really harmonic. So there is some anharmonicity involved, and I should have more terms in here. But this is about. So all the quantum numbers for the electron will be here. Now, here is the quantum number for the vibration. There is also the rotation, which is here. This is the quantum number for the rotation of the molecule. And there is a term that I did not mention very much, but imagine in your mind that when I am rotating, this will affect the vibration, right? So that is what we call a coupling, rho vibrational coupling, which means the state of vibration will be coupled to the state of rotation. And this is this term here. So we have this term, which somehow couple vibration and rotation together. And everything now is in a constant A for representing how strong is this coupling. So basically we have the electronic energy, vibrational energy that will depend on this term, and V is the vibrational quantum number that goes 0, 1, 2, 3. When V is 0, you are in the ground state. That's the best you can do. That's the best you can do. It's the minimum energy state of a molecule. It's very hard to get a molecule in that state, but normally you have a minimum energy here where the molecule stays. You have the rotation, and you have the rotation, which is given by this quantum number F, and F can be 0, 1, 2, and so on. And now we have also what we call coupling whole vibrational, which is this term here of the energy, is because there is an interaction between the vibration and the rotation of the molecule, as you can imagine. If you take a spring and start to rotate with two masses, you're going to see that this vibration depends on the state of rotation. It's basically what's going on here. Now, what's happening with all this? Well, that's how reactivity of molecules take place, is depending on the electronic energy, depending on the vibrational energy, depending on the rotational energy, you get different reactivity. Imagine a molecule that's rotated. It may react easily than when it's not rotating. Vibration, either. So all those states, even though the total energy in there, the energy that we use from molecules when we burn things, when we burn fuel, or the energy we run our own body, comes from the electron energy. That's the main source, because we saw that's big. The energy, the chemical bonds, is much more than the energy in the vibrations and the rotation. But vibration and rotations affects a lot the reactivity. Energy transfer, you can imagine two molecules getting together, depending on how they are vibrating or rotating in those bands of levels. They may transfer energy easily or harder from one to the other. And all those processes is what determine the chemical reactions, right? And the chemical reactions then is fully dominated by more than only the energy in the electron. It's dominated by many other things, the occurrence of those chemical reactions, right? So it's differ a lot. Normally the rotation is a nice way to heat up. The heat, when you heat up water, for instance, you are making vibrating more and more. Well, everything is going a little more, but mostly vibration and rotation. And when we put microwave, which is electromagnetic wave, as we saw before, the frequency is exactly the frequency to make the water to rotate. So when you put a glass of water or a cup of water in the microwave oven, you make the molecules to rotate. And then they bounce each other and they start to vibrate, and that turns into heat. And you heat up your stuff. If the molecules are very hot, they can interact more with the organic molecules of the coffee and extract the products that make us happy. Or in the tea, when you put the tea, if you put the tea in cold water, it takes a while for dissolve to extract the substance from the tea leaves, right? But when you put in the hot water, because of those vibrations and rotations, it's more efficient to extract to dissolve whatever is in the leaves, right, in the tea bag, and bring to the solution. So you see, all these things goes on because of those processes of rotation and vibration. Okay, so basically we saw the fundamentals of the atoms, and now we saw more or less the fundamentals of the molecules. Of course, this can be done in a very rigorous way. We can do very rigorous calculation on the molecules, and there are many scientists that do this for their life, and this is a serious business in chemistry and in physics, right? And in biochemistry and also in biomedical. How those things react, how they do, what they do, including the vibration of the molecules are also important in the formation of liposomes, nanotechnology type of thing. This is very important. And they are all quantum. The origin of all this is quantum mechanics. And if you want to understand a little bit what's going on in this level, you must understand a little bit of quantum mechanics. And this is the purpose of this course. Okay, we come to the end of this lecture. And the next lecture, we're going to start a topic that is how radiation now interacts with this. How can we predict energy being transferred from electromagnetic radiation to atomic or molecular levels? This is what we're going to do from the next lecture on, because that's a very nice, important application of biomedical and engineering in general. Okay, see you in the next lecture. Bye-bye.